Afternoon. So we will continue with the diagonalization topic today. Hello, good afternoon. So today we will be continuing with the diagonalization topic. So we did the diagonalization for a 2 by 2 matrix last time, and let's try a 3 by 3 matrix for the diagonalization. Okay, so for example, if the matrix is 2 0 0 9 minus 1 3 and then 6 minus 2 4. So if we want to diagonalize it, which means that we want to find some matrix P and D and P inverse. Okay. So as we know that in the diagonalization, the diagonal matrix will be the one which will consist of the eigenvalues. So we need to find the eigenvalues. So finding the eigenvalues, so we will determine the characteristic equation. So that will be the determinant of A minus lambda I that is equal to 0. So we will try to determine A minus lambda I first. So we will find the determinant of A minus lambda I. So that will be 2 minus lambda, and the other two terms are 0, 0. It will be 9, and then it will be minus 1 minus lambda. This diagonal term, minus 1 minus lambda, and then 3. And then it will be 6 minus 2, 4 minus lambda. So if we want to find its determinant, so then what we will do, we will expand it from the first row. So its determinant will be then 2 minus lambda times the determinant of this minor matrix, minus 1 minus lambda, 3 minus 2, 4 minus lambda. And then the other two elements are 0. So therefore there is no further term over here. So since this is the equal to 0, so then we can write it like 2 minus lambda, and then this is a 2 by 2 matrix, so it is minus 1 minus lambda times 4 minus lambda. So it will be minus 1 minus lambda times 4 minus lambda, and then minus 3 times minus 2. So that is equal to 0. So from here we can find find that 2 minus lambda, and then when we multiply it, so minus 1 times 4, so that is minus 4. Minus 1 times lambda is plus lambda, minus 4 lambda, and plus lambda square, then that is plus 6 is equal to 0. So 2 minus lambda and 2 minus lambda, and then this will be lambda square minus 3 lambda plus 2. So lambda square minus 3 lambda plus 2 can be factorized into, this will be factorized into lambda minus 2, lambda minus 1. Okay, so lambda square minus 3 lambda plus 2 can be factorized into this. Or in other words, we can also write this is lambda minus 2, this is 2 minus lambda. So if I take minus 1 out from here, so it will be also lambda minus 2. So that is our whole factorization will be lambda minus 2 square into lambda minus 1 is equal to 0. So in this way, then we will get the eigenvalues as lambda 1 will be equal to lambda minus from lambda minus 1 is equal to 0. So lambda 1 we will get is equal to 1, and lambda 2, lambda 3 are equal to 0 because this will be the double root. Lambda is equal to 2, that will be the double root from lambda minus 2 is equal to 0. So we can write the diagonal matrix as like this. So that will be lambda 1, so 1, 0, 0, and then 0, lambda 2, that is 2, 0, 0, and then 0, 0, and then lambda 2, 3 is also 2. So this will be the diagonal matrix. So for finding the P matrix, so we need to find the eigenvectors. So for finding the eigenvector, so we will determine, we will use the eigenvalues, and we will find the corresponding eigenvector. So for lambda is equal to 1, the augmented matrix will be 2 minus 1, that is 1, 0, 0, and then 9, minus 1, that is minus 2, and then this will be 3, and then 6, minus 2, and then 4 minus 1, that is 3. So that will be the left hand side of the augmented matrix. For the augmented matrix, 0, 0, 0. Remember that we are, for finding the eigenvector, we are looking at this condition, A minus lambda I U is equal to 0. Okay, so that results into this augmented matrix, homogeneous situation. So for this augmented matrix, so we need to apply the row operation. So it will be 1, 0, 0, 0. So multiply this first row by 9 and then subtract from the second row. So that will be 0, minus 2, 3, 0. And then multiply the first row by minus 6 and then add to this. So it will be 0, minus 2, 3, 0. And then 1, 0, 0, and then 0, minus 2, 3, 0. And now we can, what we can do is subtract the row 2 from row 3. So that will, the last one will be 0, 0, 0. So for the case of eigenvectors, this is a very normal situation. Okay, so in fact, we always want to have a 0th row for a regular eigenvector. So from this, what we can get the we can get the eigenvector as something like this. So for example, if we do the back substitution method, we can start from row number 2. So suppose the eigenvector components are u1, u2, u3. So or maybe you can say that the eigenvector components are, say, if for example this is A, B, C, if the eigenvector components are A, B, C, so it will be minus 2A, okay, plus 3 minus 2B, so it will be minus 2B plus 3C is equal to 0. Okay, so from here we can calculate B as a combination of C, so it will be 3 by 2. Okay, C. So where C is an arbitrary constant. Instead, normally we represent by S, but that is also fine. We can use anything. So it will B is equal to 3 by 2 C. And from the first equation, what we get is A is equal to 0. So that means the first component A will be equal to 0. So in this case, then we get the eigenvector that will be A is equal to 0, B is equal to 3 by 2c, and then c is equal to c. So we take c as constant, and then we can remove the fractions by multiplying throughout by 2. So it will be 0, 0, 3, and 2. 0, 3, and 2. So we multiply by 2, so it will be 0, 3, and 2. So therefore, one of the eigenvector will be 0, 3, and 2. So corresponding to lambda is equal to 2. Okay, corresponding to lambda is equal to 2. So we get a minus lambda I u. So we get the augmented matrix, something like this. So now lambda is equal to 2. So it is 0. So the first row will be 0, 0, 0. The second row will be 9 minus 3, 3. And the third row will be 6 minus 2 and 1. Sorry, 2. 6 minus 2 and 2. Okay. So from here, what we can do is, since the first row is all 0, we can apply one of the allowable row operation, that is interchange the row. So we can interchange the row 1 and row 3, okay, over here, so that there will be no problem with that. The solution will remain the same. Okay, so it will be 6 minus 2, 2, because it is an allowable row operation. So 6 minus 2, 2, 9, 9 minus 3, 3. Second row remains the same, and the last row is 0, 0, 0. Because we want some proper pivot position values on the diagonals. So, and yeah, I forgot to put those 0, 0, 0, although those 0, 0, 0 will not make any difference over here. So that will be the augmented matrix. And then from this augmented matrix, so what we can do is we can further simplify it. So 6 minus 2, 2, so we will divide it by 6. So it will be 1 minus 1 by 1/3, 1/3, 0. And then it will be 9 minus 3, 3. So I am taking one step at a time, okay? So I divide the first row by 6, okay? Row 1 by 6. And now I multiply the first row by 9 and subtract from the second row. So it will be 1 minus 1/3, 1/3, 0. And then it will be 9 minus 9, 0. So I take the, so this will be by multiplying it by 9, it will be minus 9, it will be plus 3. So plus 3 and minus 3. So it will be plus 3 minus 3, that will be 0. Okay. And then and then 0 again. So because this will be minus 3 plus 3 is 0. So it will be 0. And then the last row was already 0. So now we get 2 0 rows over here. Okay. Which is also normal over here, because in this case we found that lambda minus 2 was a double row. And we have earlier used a term which is called as the multiplicity. So the multiplicity of this is 2. So in this case, for the eigenvector case, it is normal to have those 2 0 rows over here. So that we will have two-dimensional base of this eigenspace. Anyway, so only significant equation is the first one. So first one is the, if for example, if you take U2 are like D, E, F, okay? So what will be those constants? So D, E, and F, okay? So from the first equation, what we get is D minus 1/3 of E plus 1/3 of F is equal to 0. So now E and F, we can represent D as D as like 1/3 of E minus 1/3 of F. So where E and F are now the arbitrary constant. So therefore, U2 will be what? U2 will be 1/3 of E minus 1/3 of F, 1/3 of E minus 1/3 of F, and that will be E will be E over here, and F will be F over here. So now I have run out of space in this slide, so I will move it to the next slide. So I rewrite U2 over here. So what we got over here was 1/3 of E minus 1/3 of F, that is E and then F. So this can be written as something like this: E times 1/3 1 0 and plus F times 1 minus 1/3 0 1. Okay, so we can write it like this. We can remove this these fractions for convenience. So E, so we can multiply it by 3. So it will be 1 3 0, and then plus F. So it will be, we can also remove its fractions by multiplying it by minus 3. So it will be 1 0 minus 3. Okay, 1 0 minus 3. 1 0. So what we get, we got two dimensional eigenspace, okay, for the base. So 1 3 0 and 1 0 minus 3. Remember that if we choose instead of 1 0 3 minus 1 0 3, then it would also be correct also. So therefore, what we get for a P matrix, that is the that is one we needed. So P matrices now for the first we got for corresponding to lambda 1, lambda is equal to 1, we got 0 3 2. Okay, 0 3 2. So it will be 0 3 2, and then corresponding to lambda is equal to 2, we got two components. So 1 3 0 1 0 minus 3. Okay, so in this case we have got a proper P matrix over here. So 0 1 0 1 1 3 3 0 2 0 minus 3. Okay, remember that if in this case for some of the matrices when we have a double root from the characteristic equation. So for example, in this case, double root from the characteristic equation, and then when we try to find the eigen vector, we don't get these two rows, 2 0 rows, we only get maybe 1 0 row. So in that situation, there will be only one eigenvector. There will be no two eigenvectors from this double root. So when we get only one eigenvector from that double root, then that means the other eigenvector does not exist. So in that case, we can say that that matrix and that situation is the situation when we cannot diagonalize that given matrix A. We will see that example in the next So, but let's complete it first. So remember that now we have already found P. Now what we need to find is P inverse. Okay. So for P inverse, since this is a 3 by 3 matrix, and then this we need to find. So we can use some method which is known to us. The most convenient method is the row operation. So for the row operation method, because this is a 3 by 3 matrix, and then here is one thing which we can see from here. So we can write it like this first: 0, 1, 1, 3, 3, 0, 2, 0, minus 3. And then that will be the augmented matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1. So this will be the augmented matrix. So we augment it with the identity matrix. Okay, so from here we need to apply some row operation. But here for the row operations, what our line of action is, we take the first column and then in the from the after the first row, the second row and the third row elements we want to make 0. But in this case, in this type of situation, we cannot make these 3 and 2 as 0, because by anything, if we will multiply this first row, this 0 will remain 0, and then we cannot make it 0. So in this case, what we will do is we will apply another allowable row operation, that will be the interchange of the rows. Interchange. So what we can do is we can interchange row 1 and row 2. So 3, 3, 0, 0, 1, 0. Okay. So this will not make any difference, okay, to the inverse matrix. So because this is an allowable row operation. So 0, 1, 0, 0, 1, 1 will be now in the second row. 0, 1, 1 in the second row. And then it will be 1, 0, 0. And now what we get is 2, 0, minus 3, and then 0, 0, 1. Okay. Okay, so the next row operation will be, because this is already 0, no, but this should be 1. The first row should be 1, so it should be then 1, 1, 0, 0, 1 by 3, 0. And then the first row should be 1. Then the second row will be, the second row is already 0, 1, 1. Okay, 0, 1, 1, 1, 0, 0. And then it is 2, 0, minus 3, 0, 0, 1. Okay, so this is how the operation will go. So now we will make this, this number as 1. So for this, what we will need to do is we will need to multiply the first row by minus 2 and then add to the third row. So it will be, okay, 1, 1, 0. And then it will be 1, 1, 0. And then it will be 0, 1 by 3, 0. That remains the same. Second row will also remain the same, 0, 1, 1, 1, 0, 0. And then it will be now become 0. This will be minus 2 because we multiplied it by minus 2. Minus 2 plus 0 is 1. And then this will be minus 3, this first column. And then it will be 0. And then it was multiplied by 2, minus 2 by 3. So it will be minus 2 by 3. And then this is 0. And then that was 1. So this remains as 1. Okay. So now we get this. So after this, the next step is we want to make this element as 0. Okay, we want to make this element as 0 because this was minus 2. So for this, what we will need to do is we will multiply the first row will remain the same. Okay, 1, 1, 0, 0, 1 by 3, 0. And that is 0, 1, 1, 1, 0, 0. And then it is 0, 0. Second row will be multiplied by 2 and add to the first third row. So that will be 2. 2 minus 3 is minus 1. Okay, minus 1. And then 2, and then 2 plus 2, 0 is 2. 0, so this will be minus 2 by 3. And then it is 0, and then it remains as 1. Okay. So what is the next operation? Because this is -1, this should be +1. So what we will do is we will multiply the last row by -1. So it will be 1, 1, 0, 0, 1 by 3, 0, 0, 1, 1, 1, 0, 0. It will be 0, 0, 1, -2, 2 by 3, and -1. Okay, -2, 2 by 3, and -1. Okay. Now there will be still some more operations left. So now we have this as a lower triangular matrix, but we have to make it as also as the upper triangular. Lower triangular as well. It is already an upper triangular. We have to make it as an upper triangular as well. So we need to make this one as 0. So what we need to do is the first row remains the same, 1, 1, 0, 0, 1 by 3, 0. So for this we need to do is we will subtract the row number 2, row number 3 from row number 2. So it will be 0, 1, 0, because 1 minus 1 will be 0. 1 minus 2, 1 minus -2, it will be +3. So it will be +3. And then 0 minus 2 by 3, that will be -2 by 3. And 0 minus -1, that will be +1. Okay. The last row is written like this. So -2, 2 by 3, -1. Okay, so then one more step and then we will be done. So now we want to make this as 1 because this is already 0. So this is, so what we will need to do is we will subtract the row number 2 from row number 1. So it will be 1 minus 0, that is 0. 1 minus 1, that is 1. 0 minus 0, that is 0. 0 minus 3 is -3. And 0 minus 3 is -3. 1 by 3 minus -2 by 3. So 1 by 3 plus 2 by 3, that is actually 1. And 0 minus 1, that is -1. Okay. And then what we have is the second row and the third row, which will remain the same. Okay. So if we have not done, if I have not done any calculation mistake, so this should be the inverse matrix. So P inverse then therefore is on the right hand side of the augmented matrix. So it should be then -3, 1, -1, 3, -2 by 3, 1, -2, 2 by 3, -1. So we can verify it. So it is -3, 1, -1, 3, -2 by 3, 1, -2, 2 by 3, -1. So we can verify it by the multiplication. So P inverse should be equal to the identity matrix. So anyway, in this case, we have used the 3 by 3 matrix to diagonalize it. So therefore, what we can say is that our final answer is final answer. So initially we had this matrix A. Okay. So initially we had the matrix this one, 2, 0, 0, 9, -1, 3, 6, -2, 4. So from this matrix, we have got a matrix P, which was 0, 1, 1, 3, 3, 0, 2, 0, -3. And the diagonal matrix. So the diagonal matrix was 1, 0, 0, 0, 2, 0, 0, 0, 2. And the P inverse matrix, which we just got, is -3, 1, -1, 3, -2 by 3, 1, and -2, 2 by 3, -1. So this is the answer. And of course, we can verify this answer by the multiplication of the matrices.
Sorry, could you please just show one more time the diagonal, how the matrix was diagonalized, like 1, 2, 2, in the previous slide, just the previous slide.
In the previous slide, okay, let me go to the previous slide. Where is this? Yes.
Ah, oh, okay.
Yeah.
Yeah, thank you.
So for the diagonalization of the matrix D will contain the eigenvalues.
Okay, okay,
Because the matrix P will contain the columns of the eigenvectors. Okay.
okay, okay.
So as you can see that the process for the calculations involved for the 3 by 3 matrix are quite a lot, if you will, if you want to do it. If for example, if it is a 2 by 2 matrix, that we can do it relatively quickly. Okay, so remember that in this case, the matrix A was diagonalizable, but not every matrix is diagonalizable. Okay, so we see one example of that. For example, if the matrix is matrix A is 17 minus 3 minus 21 minus 3 1 5 12 minus 2 minus 50. So of course, from this matrix, we cannot tell, by just looking at this matrix, we cannot tell that it is diagonalizable or not. So we have to make some calculations to check whether it is a diagonalizable, or whether it is diagonalizable. So 17 minus 3 to minus 21, it is over here is minus 3, 1, 5, 12 minus 2 minus 15. Okay, so to check whether this matrix is diagonalizable, so we need to first find the eigen values. So for finding the eigenvalues, so we need to write the characteristic equation. So the characteristic equation will be from here. It's the characteristic equation will be the determinant of this 17 minus lambda minus 3 minus 21 minus 3 1 minus lambda 5, and then 12 minus 2 minus 15 minus lambda. Okay. Okay, so next we need to find its determinant. So we can expand it from the first row. So it will be 17 minus lambda, and then its minor matrix will be 1 minus lambda, 5 minus 2 minus 15 minus lambda, and then the sign will be minus, plus minus plus. So it will be minus 3 times its minor matrices, minus 3, 5, 12, and then minus 15 minus lambda. Okay. And then the next sign is plus. So it will be plus then minus 20. Minus sign is the original, then the plus is for the cofactor. So it will be minus 3, 1 minus lambda, 12 minus 2. Okay. So this can be written as because this is 17 minus lambda, 17 minus lambda, and then if you will so if I simplify it, this determinant, so this determinant will be lambda square plus 14 lambda, okay, plus 14 lambda and minus 5. I am skipping some calculations, but this will simplify into this. And then plus 3, this will be minus minus plus 3. And this will simplify into this will simplify into 3 lambda minus 15. And then this is minus 21. And then this will be simplified into 12 lambda minus 6. Okay. And
I'm sorry, but shouldn't it be 3? Sorry, yeah, that's correct. 3 by 15 multiplied. Yeah, that's correct. I'm sorry.
yeah, because I'm
Maybe
skipping some steps, so that's why.
Okay.
You can check it later, but I think it is correct. Okay, so now this equation will further simplify into minus lambda cube plus 3 lambda square minus 4. Okay, so this will be a cubic equation. So I think there is no direct solution to this equation. So by trial and error, you can find the solution. Okay, so by trial and error. But in this case, since we have chosen the values in such a way that we will get the integer values, so we can easily find its solution, something like this. So its solution will be something like this. So if we equate it equal to 0, so this equation will be something.
-1 can sit.
Sorry.
We can use -1 as one of the roots.
Yes. So this will factorize into like this. So therefore, -1 will be one of the roots. But the other root will be the 2. The other root will be the 2. So we will say that by trial and error, something like this, we can find this solution. So one of the root is lambda is equal to 2. So this is the double root. Okay, double root. And the other root is lambda is equal to -1. So here actually one thing which I want to give as a tip is that, so whenever you find a double root, then maybe you can try to find the eigenvector corresponding to the double root first. So that will give you an indication that whether that matrix is diagonalizable or not. We did not do in the previous case. In the previous case, it was also a double root, but we could have done that in the previous case as well. Because in the, with the double root, there will be a chance to determine first whether this matrix is diagonalizable or not. Okay. So if we use this single root to find the diagonalization for this process, then we may not find it. Okay. So anyway, so in this way we can save our time. So in this case, we try this lambda is equal to 2 first. So remember this condition. Okay. Sorry, times u. Remember this condition for finding the eigenvector. So what we do is a minus lambda I. So we use lambda and then we will try to solve it. So to solve this augmented symmetric situation. So we're using lambda is equal to 2. Okay, use. Then we find this 17 minus 2 is 15. Minus 3 minus 21. and then -3, and 1 minus 2 is -1, 5, and then 12 minus 2, and then -15 minus 2 is -17. And then if we equate it to 0, so we get this augmented matrix. So what we can do is, so we can first we divide, maybe we can interchange these rows, so that then that will give us maybe better. Okay, so we can, and also we can multiply the second row by -1. So it will be 3, 1, -5. So it will be 3. So it will be 3, 1, -5. Yeah. So it will be 3, 1, -5, 0, and then it will be 15, -3, -2, -21, 0. Okay, 15 minus 3 minus 21, 0. And then it will be 12 minus 2 minus 17 is equal to 0. So now what we can do is we can, there is no need to convert this into 1. We are not converting this into 1 is useful for when you are finding the inverse, but we just, when you just want to make it into the echelon form, there is no need to convert this 3 into 1. So it will be 3, 1, -5. Okay, so let me check it. So if it everything is correct, so it was 15 minus 3 minus 21 minus 3 minus 1, 5, because 1 minus 2 was -1. Okay, 12 minus, so 12 minus 2, and then -15 minus 2 minus 17. Okay, and then I interchange these rows, so it will be, and then simultaneously I also multiplied the first row by -1. So it will be 3, 1, -5. Okay, and then 15 minus 3 minus 21, and then 12 minus 2 minus 7. Okay, it seems to be correct. So 3, 1, -5, 0. And then what we get over here is, so from here, so what we do is we multiply this first row by -5 and then add to this. So it will be 0. And then it will be, so by multiplying, so we multiplied by -5, so it will be -15, -5, okay, and then it will be 25. So now 15 minus 15 is 0, -3 minus 5 is -8, so it is -8. 25 minus 21 is +4, and then this is 0, of course. And as a next step, we multiply by -4. So it will be -12, -4, 20. Okay. So now it will be 12 minus 12 is 0. -4 minus 2 is -6. So -4 minus 2 is -6, and 20 minus 17 is 3. So this is 0. Okay. So now what we have is 3, 1, -5, 0. And then from here, what we can do is 0, -8, 4, 0. And then you can see that, yeah, we can see, but we can do one more step over here. So if we want to make this as 0, so what we will do is, so we will multiply this by, so for example, if we multiply this first row by -3, so it will be 0, 24, okay, 0, 24, minus 12, and then 0. And then this third row by 4. So it will be 0 and if we multiply this second row by say 3, so it will be minus 24 plus 12, okay, minus 24 plus 12. And then the second row by 4, so it will minus 4, okay, anyway, so it will be minus 4, so it will be plus 24 minus 12 is equal to 0. So now we can add these two. So what we'll get is 0 and 0 and 0 over here. Okay. So in this case, for lambda is equal to 2, now we get is 0 minus 8, 4, and 3, 1 minus 3 minus 1, 5. Okay. Minus 3 minus 1, 5. So here we can, what we get over here is a solution which is so we can get so from this row has become 0. So 3, 1, minus 5, 0, minus 8, and 4. So from this from the second row, what we get is minus 8 times if, for example, u is a, b, and c. So minus 8b plus 4c is equal to 0. So from here we get b is equal to c by 2, right? B is equal to, so b is equal to c by 2, okay? And then from the first equation, 3a plus b minus 5c is equal to 0. So if we put 3a plus b, which is c by 2, and minus 5c is equal to 0. So what we get over here is 3a, so minus 5 plus c by 2, so that is equal to minus 9 by 2, so minus 9 by 2 c. So from here we will get a is equal to 3 by 2 c, okay, 3 by 2 c. So therefore our matrix will be what? Matrix U will be this A is 3 by 2 C, B is C by 2, and C is C. So matrix A, let me write it. I mean, I have lost some some space. So let me write it over here, okay? It's very messy over here now. So it is, and then we can remove these fractions by multiplying by 2. So it will be C times 3, 2, 1. C times 3, 2, 1. So now we can see that this is the
sorry, shouldn't it be 3, 2, 2? Because the last row C is just a 1. So if we multiply by 2, so it should be 2.
Okay, yeah, okay, yeah, okay.
So maybe 3, 1, 2.
It's 3, 1, 2? Okay.
Yeah, it should be 3, 1, 2.
Okay, yeah, that's good. Okay. Any case, let me correct it. So it is okay, I try to write it nicely. 3, 1, and 2. Okay. So multiply by through 3, and then 2, it is 1, then 2 is 2. So 3, 1, 2. So now what we see over here is, so not what we see over here is a eigenvector. Okay. So, but actually we started from a double row. A double root. Okay, we started from a double root, but we only got a single dimensional eigenspace vector. So in this case, for the double root, it was required to get a two-dimensional eigenspace. Okay, so we can say that the dimension of the eigenspace is strictly less than the multiplicity of the eigenvalue. So, for example, the multiplicity of this root was 2 because it was a double root. So, for a double multiplicity root for a proper diagonalization process, we should get two components, but we only get one component of the matrix. So we can see that this is a one-dimensional. The dimension of the eigenspace is 1 over here. So in this case, for example, if we should have got something like this. This S1 plus S2, something like this. If we got something like this answer, then we could say that A was diagonalizable. But in this case, this part is missing. We cannot get it from here. We only got one eigenvector over here. So we can simply say over here is that this matrix is not diagonalizable. Okay.
I have a question. So
Yes.
basically, when we want to diagonalize a matrix, we should
Yes.
first find the eigenvalue, our
Correct.
eigenvalues, and
Yes.
then we should look on the highest rank, highest multiplicity root.
Yes.
Yes.
Correct. Correct.
And if this root will not give us the exact number of, let's say, the subspaces or the eigenvectors,
yes,
then it means that the matrix is not diagonalizable. Yes.
correct. Yeah, you understand correctly.
Yeah. Yeah.
Yeah. All right. So yeah, I think today it was a little bit slow. It's because the questions were a little bit longer. Originally, I wanted to cover some more questions as well, but I could not do it. So the next actually topic was the complex eigenvalues. So, but
I have a question. What if we have like not the double? Can we have from the 3x3 matrix have a triple root when we are trying to find the eigenvalues, like triple root?
yes, it's a possibility. Yeah. Yeah.
Oh, okay.
It
So
is
then we
also.
also should find like
Yeah,
three eigenvalues.
yes. So the triple root, that means it will be a complete cube, the characteristic equation.
Okay, and is it possible to have an eigenvalues that are not integer?
That are not integer?
Integers, yeah.
Yeah, yeah. Eigenvalues can be any real number, integer or rational or irrational, whatever.
Okay.
Even the complex,
So
but the complex case we have not considered yet.
So it will just like make the dimensions very like complex. It will increase the complexity of the dimensions. Yes.
Yeah, the calculations will be complex, so that's why we carefully choose the matrices so that we are only dealing with the integer values. Otherwise, it's not necessary.
Okay, thank you.
Yeah, okay.
So can I ask about final exam?
Yes.
Solve only 5 questions, and it's not necessary to solve the one more, yes? And we will not get